Today, we'll discuss the cell bioelectricity phenomenon. First, let's take a glance at the concept. Electrical change appear at living tissues such as muscles, nerves, and glands before this tissue action. It's one important and one basic phenomenon. First, let's come to resting potential and the genesis mechanism of resting potential. The potential difference across the membrane at the rest stage or when the cell was not stimulated. Its properties include it is constant, its negative inside relative to the outside. Resting potential are different in different cells. For the muscle cells, resting potential are minus 90 millivolts. For the nerve cells, 70 millivolts. And for the red blood cell, only 10 millivolts. Let's see the polarization. We take the extracellular potential for 0. So the intracellular potential equals negative value at rest. For depolarization means the absolute value of voltage decreased. For hyperpolarization, the absolute voltage value increased. Example from 70 to 80. Repolarization means the return to rest potential after depolarization. Reverse polarization means depolarize to positive. Overshoot means the voltage is over 0. It's very important for the genesis mechanism of resting potential. First, the intracellular potassium concentration is higher than extracellular. So there's a concentration gradient. We know for the intracellular, it's about 155 millimolar, and extracellular only 4. The cell membrane is permeable to potassium at the rest stage, so the potassium ion diffused through the cell membrane. Let's see the image. The extracellular has lower potassium concentration and the intracellular has higher concentration. So the flow of potassium from intracellular to extracellular can genesis the about 70 millivolts voltage. This can conform the resting potential voltage. In one sentence, potassium ions concentrate inside the cell tend to move outward down their concentration gradient through non-gated potassium channels. But the membrane potential resists potassium diffusion, so there's an equilibrium. When the electrochemical driving force is 0, the diffusion stops. That means the potential difference across the membrane is in potassium equilibrium potential. The resting potential can be calculated according to the Nernst equation. When the temperature is 29 Celsius degree, the resting potential equals minus 77, and the potassium equilibrium potential is minus 87 millivolts. The reason there's a difference between EK and the resting potential is because the cell membrane has some extends permeably to the sodium ions at rest. So resting potential measured value smaller than calculated value. Since the resting potential is less than potassium equilibrium potential, a little continuous potassium outward flow and sodium inward flow at rest. That's all for the resting potential. Now we move to the action potential, AP, and the genesis mechanism of action potential. The definition of action potential is it's a rapid, reversible, and conductive change of the membrane potential after the cell is stimulated. The basic form is upstroke, that means depolarization. The resting potential got local potential, and once the local potential reached the threshold potential, the cell got depolarization and then got overshoot above 0 millivolts and got spike-like potential that formed the action potential, also got the cell got excitation. After the upstroke, there's a downstroke. The cell needs repolarization. We know it's reversible. It's a rapid repolarization and slow repolarization of the potential. It have negative after potential and also positive after potential. That means after hyperpolarization. The characteristic of action potential of a single cells, it is all or none. It is non-decline propagation. It cannot be summarized. Let's see the genesis mechanism of action potential. It includes a inward current, outward current, and depolarization. First, the force for this process comes from electrochemical driving. The stimulation makes the cell membrane suddenly increase the permeability to sodium. The sodium ion channel opens very fast. So the sodium ions flow from extracellular to intracellular in fast way and reach an electrochemical equilibrium. So opening of sodium channel cause a sodium equilibrium depolarize towards the E sodium. So we got action potential overshoot and the same equation with NERST. This is the properties of channels. The sodium channels. It's a fast channel. It depends on the voltage. It has the resting state, activate state, and inactivate state. Generally, it's closed, but in resting stage, when there is depolarization triggered, the channel opened in very fast way, and before repolarization, the channel become inactive state. So repolarization is a very important stage. At the end of depolarization, the sodium channel closed, potassium channel opened, and the potassium ion from the intracellular to extracellular flow. So there's a downstroke of action potential process called repolarization. And at the end of repolarization, the sodium pump began to work against the concentration. The cell restored to the resting potential. So let's see the whole process of acting potential, the resting potential to action potential, and the repolarization stage. For the yellow color, that's depolarization stage. The sodium channel opened, and more sodium channel opened makes the overshoot up to around 30 millivolts, and that's the green stage. And after that, the sodium channels closed, and the potassium channel opened, and then after the repolarization, the potassium channel closed again. The cell restored to the resting stage, rest potential. So let's take a summarize for the action potential generation. In the proper stimulus, the opening sodium channel got depolarization. After the inward sodium current, the closing of sodium channel starts the repolarization process, opening of the potassium channel, and the outward potassium current restore the resting potential, the resting state of the cells. So there's a method called voltage clamps. This can measure the current. That means the conductance for sodium and potassium. The increase of conductance of sodium make the sodium inflow forming depolarization. The increase of conductance of potassium make the potassium ions outflow forming repolarization. Because of the single channel current is very, very small, so we need all the cells, all this channel together to make a bigger current. Let's see the conductance of sodium and potassium. It can make up to 30 millivolts, and to this extent of current and voltage. Now let's move to the local potential and the threshold potential. We know when the stimulus to reach the threshold potential to trigger the depolarization, there is a local potential and reach the threshold potential. The local potential, also called graded potential, it is a depolarization. It's a kind of depolarization. The resting potential value decreased. That means the absolute value decreased. The difference between the local potential and the active potential is the number of sodium channel opened. When it is very near the threshold potential and reach the threshold potential, that means critical membrane potential that can elicit the active action potential. That means the sodium channel opened suddenly. Generally, it is less than 10 to 20 millivolts than the resting potential. It can trigger the sodium ions flow into the intracellular. That means excitation. Let's see the definition of local potential. It is a local response. It's a very small change in membrane potential caused by subthreshold stimulus. It is a graded potential. It is propagation is electronic conduction. It can be summed by two ways, spatial summation and temporal summation. The role of the local potential, it can facilitate the cells. This means it increases the excitability of the stimulated cell. It can cause the cell to excite once it is summed to reach the threshold potential. It can be summed up. Now let's move to the propagation of action potential. Quite different for the non-myelin fiber and the myelin neural fiber. First, we move to the non-myelin neural fiber. The local current formed, there's a non-excitation part is stimulation. We've got depolarization, got local potential, a sum up can trigger threshold potential, got action potential. The action potential is bilateral directional propagation along an axon. It's quite different with myelin neural fibers. This picture is very simple for us to understand. Tell us the propagation of the action potential. The sodium flow depolarizes the membrane, and the positive charge flows into the adjacent sections of the axon by local current flow. In the distal parts of the axon, the local potential can cause the new section of depolarization. But for the myelinated neural fibers, it's quite different. We call it saltatory conduction is the mainly form of the transportation. The action potential jumped from node to node. It also is a direction propagation. The pattern of the conduction in the myelinated nerve fiber from node to node is called saltatory conduction. It is of value the following two reasons. It is very fast and it conserves energy. It just consumes very small energy. The factors that affect the propagation include the cell radius that will affect the resistance and the density of sodium channels, the myelination, and the velocity and amplitude of the membrane depolarization, and the gap junction will also affect the propagation. Let's make a summarize. Let's compare the action potential and local potential. For action potential, it is all or none phenomenon, but for local potential, it's not all or none phenomenon. For action potential, it's non-decline propagation. The local potential is electronic propagation. AP has refractory period, but for local potential has not refractory period. Action potential cannot be summed up, but local potential can temporal summation and space summation. The excitation and excitability of the tissues. The definition of excitation is property of action potential or process of action potential generation. Excitable cells, the cells which is able to produce action potential. That include nerve cells, muscle cells, and granular cells. The excitability, the capacity of the cells to generate action potential in response to a stimulus, any kind of stimulus. The requirement for cell excitation include excitability. The stimulus, any change in environmental surrounding the cells can form the stimulus. And the parameters include the intensity, also called the strength of the stimulus, and the duration of the stimulus, and the changing rate of intensity. Another definition of this part is threshold intensity, also threshold value. The lowest intensity of stimulus to induce action potential reversely proportional to excitability, measure index excitability. Threshold stimulus at threshold intensity. There is a supra-threshold stimulus and sub-threshold stimulus. For the supra-threshold stimulus can cause AP, but sub-threshold stimulus cannot cause action potential. Now let's move to excitability cycle change after excitation. There is an absolutely refractory period. That means excitability equals 0, and relative refractory period. The excitability is bigger than 0, but is lower than the normal excitability. It needs supra-threshold stimulate can cause the action potential. And supernormal period, that means excitability above normal stage. It just need a sub-threshold stimulus can cause the action potential. And subnormal period, the excitability smaller and below normal, also need super threshold stimulus. This picture we are very familiar already. We use this kind of picture to different stage of the resting potential, the depolarization, the repolarization. This picture now told us the refractory period got absolutely refractory period, and from when sodium gate are open to just after they closed. This time, this very short period of time called refractory period, absolutely refractory period. And there are also relative refractory period. It lasts until the potassium gate closed and the membrane voltage returns to the threshold. The neuron will respond to additional stimulation if it is strong enough. That means relative refractory period. Absolutely refractory period is very short. But for example, for the nerve fiber, only smaller than 2 milliseconds. If the absolutely refractory period is 2 milliseconds, numbers of action potential per second, the upper limit is 500. Let's see the factors that affecting cell excitability. First, the resting potential. The absolute value of resting potential is most important factors. When the absolute value of resting potential decreased, in one condition, when the potassium of concentration out the cellular, the extracellular potassium concentration increased, the difference between intracellular and extracellular potassium decreased. The potential will decrease and the cell excitability will increase. The other factors that affect excitability is threshold potential. When the threshold potential level moved up, the cell excitability decreased. Last, sodium channel state also can affect the cell excitability. And that's all for today's class. Thank you all.